So we were talking about the single cycle. So assume that we have these example delays for different components. So instruction fetch, let's say it takes 200 picoseconds, register read takes 100 picoseconds, ALU 200 picoseconds, and memory also 200. So what do you think what should be the clock cycle period? 800. Why 800? Because LW is the slowest one. If we set the cycle time should be 800 picoseconds. Everybody get that? If we set the cycle period to, let's say, 600 picoseconds, so R type instruction could be finished, could be executed in one clock cycle. BQ can be finished. SW cannot be finished because the cycle period would be finished in 600 picosecond. LW can also be not finished. Okay, so that is why we need to set the cycle period which could accommodate the the slowest instruction. Okay, so that is why 800 picosecond is this one. What problem do you see in here? What do you think? Is there any problem? If we are so let's go for the common case. So if you are writing a loop to increment a variable, there is a variable stored in register. Okay, let's say it's register x5. Okay, so you are running a loop 100 times, and every time the register value is incremented. So what do you think? What type of instruction would it be? You are incrementing it by 1. Let's say x equal x5 equal x5 plus 1. Is it R type? What is the second input? Immediate, right? So it's an kind of like, you can say that's or if I have, let's say, A equals 1, and if I write it A here, then it becomes the R type completely. Both inputs are R operands. So which means that every instruction would be completed within 600 picosecond in every execution of the for loop, right? But what do you see? The cycle period is 800 picoseconds. So once the instruction is completed in 600 picosecond, it has to wait for 200 picoseconds to start executing the next instruction again. So clearly there is a performance issue. Just like I gave you, you're going to see 10 questions in your exam, and 30 minutes as the duration of the exam. And if I say that you have to attempt one question in 3 minutes, okay? You cannot start the next question before the 3 minutes lapsed, okay? And what if you complete the first question in 30 seconds? Will it not be a wastage of your time, right? So same as the thing here. It has to wait for 200 picoseconds. And if you have if you're running a loop for a million times, then you can imagine how much performance deterioration it will cause. Okay? So clearly, longest delay determines the clock period. So the longest path, which is called the critical path, is determined by the LW instruction, which goes through the instruction memory to register file, and then ALU, then read the data from data memory, and store it into register file. Okay? So this is the longest path of the instruction execution, which is taken by the LW instruction. Once we design the circuit, it is not feasible to vary the cycle period for different instructions, because if you remember when I was discussing the clock topic, I told you that the clock is generated by a circuit called clock generator. It will keep toggling the circuit after every certain interval of time. So if it is 800 picosecond, it will keep generating the signal 1 and 0 every 800 picoseconds, every 400 picoseconds to complete the 800 picosecond cycle. Okay? So we cannot vary the clock period for different instructions, which violates the first design principle that we studied in the very beginning, the chapter 1, that making the common case faster. If you remember, rather than going to the register and reading the value, we intended to make the common case faster by introducing the immediate value. Okay, so that was our intention. But here we cannot actually make the common case fast because of this limitation. So how do we improve the performance? Is through something which is called pipelining. But before that, let's talk about or let's assign every stage a name. So we split the entire execution into 5 different stages. The first is called IF, which is called the instruction fetch from memory. When we fetch the instruction from memory, then we have the instruction decode and register read. This is the phase where the instruction is decoded and the register is read. Okay. Then we have the execution phase where the instruction is executed on ALU, and then the memory access phase where the data is accessed from the memory, and the last phase is called write back, which writes the results back to register. Over the time, I will be only referring to like IF, ID, X, MEM, and WB terms to refer to these stages. Okay. So we have already seen that the instruction does not need to do all the stages at the same time. So for example, we are running LW instruction, let's say. Okay. So LW instruction is fetched from the memory, and when it is in the register file phase, the instruction memory remains idle. Okay. Similarly, when it reaches to ALU, both of these components remains idle. They are not doing anything. Okay. So in order to make use of that, what we do is we imply the pipelining. So one instruction, when it moves to the next phase, we start fetching the next instruction, or let the next instruction goes into the previous phase stage. Okay.